We are going to discuss now different types of ADCs, but in detail we're going to discuss one ADC in this chapter, in this course, which is Flash ADC. But to give you some introduction to of ADC circuits, of course, we discuss what an ADC is. An ADC is an analog to digital converter that converts an analog signal into digital signal. There are certain stages through which a signal goes through before a digital code is generated, and those steps are: first, the analog signal is sampled, that is, different points of the analog signals are collected at specific time instances, which are called sampling time. Once you have samples of the signal, then each sample is converted into a quantized value. It's an analog value, it's called quantized value, and the job is done by what we call a quantizer, which is part of an ADC. And the quantized value is basically an analog value that is that does not have infinite precision. It has precise value. Its precision is based on how many bits you are using for ADC. So for example, if you are using a 4-bit ADC, and if the reference voltage of ADC, that's the maximum value that can be converted through an ADC, if the reference voltage is let's say 10 volt, then you can have 2 to the power 4 16 levels. So this 10 volt will be divided into 16 levels, and each level will have its analog voltage, and that voltage is called quantized voltage. To make it simple, let's say you have 2-bit converter and your reference voltage of an ADC is 10 volt. So 2-bit means you can have 4 levels, 2 to the power 2, right? So if you divide 10 by 4 is 2.5. So you can assign a level to the sample, any sample. You can assign 4 levels. You can assign 0 volt, you can assign 2.5 volt, you can assign 5 volt, and you can assign 7.5 volt. So you have 4 levels: 0 volt, 2.5, 5, and 7. So these are called quantized voltages or quantized levels. And once you have assigned each and every sample to one of these quantized value, then you basically generate the digital code. For example, 0, it's a 2-bit converter, it will be 0, 0. 2.5, 0, 1, 5, 1, 0, and 7.5, not 7, sorry, 7.5, 1, 1. So you assign each level a corresponding digital code. So that's the basis. That's how pretty much every ADC works. Okay, now specifically how does a Flash ADC work? So before we discuss Flash ADC, let me remind you, when you took Digital Systems 2, you discussed 2 different types of ADCs, or at least 2 different types of ADCs, which were digital ramp ADC and successive approximation ADC. Digital ramp ADC, basically, just a gist of that, I'm not going to go over it, but what you do is, like I just showed you, this is a ramp, a digital ramp, right here, what I showed you. So basically, if it's a 2-bit converter, you make, and let's say my value is let's say 8 volt. Analog value that I want to convert is 8 volt, which will be somewhere over here. So in digital ramp, what we do is we go towards that 8 volt, creating this staircase ramp. And then when I get to 7.5 volt, of course 8 volt will be assigned to 7.5 volt, because there is no other voltage which is closer to 7.5, which is closer to 8 volt than the then the only voltage that is closer is 7.5. So 8 volt will be assigned to 7.5 level. So I have to create a ramp up to 7.5 volt to get my quantized voltage and my digital code corresponding to 8 volt. So each of this step takes one cycle, one processing cycle. So based on what voltage you are converting, either it can take more cycles based on where that voltage is located on the digital RAM, or it can take less cycle. For example, if you want to convert only 1 volt, then 1 volt is closer to 0 as compared to 2.5, then it's just going to be one cycle because that 1 volt will be assigned a 0 value, right? So that's the digital RAM, that you have to create a RAM to get to that voltage, and each step of the RAM takes one processing cycle. The second that you discussed in Digital Systems 2 was Successive Approximation ADC. So let's say your ADC is 2 bits or 3 bits, whatever, let's say 3 bits, right? So your values can go from 000 digital values to 111, total 8 values. So how does successive approximation works? Basically, you give an input voltage for the voltage that you want to convert into the digital code. That voltage is converted into quantized voltage, and then basically the first bit, this is, let's say, bit number 2, the most significant bit, this is bit number 1, and this is the least significant bit, bit number 0. So the most significant bit is converted from 0 to 1. So in the first cycle, it's or let's say first half of the cycle, it will become 100, and then this will be converted into the quantized value, and it will be compared against your input voltage. If this value is greater than the input voltage, then the most significant bit 1 that you change from 0 to 1, you change it back to 0. So in the first cycle, you will decide that the most significant bit either is going to be 1 or it will be 0. If the quantized voltage is less than the given input voltage after you change the first bit to 1, then you leave it to 1. You don't change it back to 0. So basically in the first cycle, it will be decided if the most significant bit will be 1 or 0. Likewise, in the second cycle, bit number 1 will be decided if it will be 0 or 1, if you want to keep it at 1, or if you want to convert it back to 0. And likewise, in the third cycle, bit number 0 will be decided if it will be 0 or 1. So for successive approximation ADC, it takes the same number of cycles to convert an analog signal into digital signal as the number of bits, right? So if it's an 8-bit converter, it will take 8 cycles to produce a digital code. Whereas for the digital RAM, if it's an 8-bit converter, you have 256 levels, 256 of these staircase levels. So if your input voltage is close to the 256th level, then it's going to take you 256 cycles to convert the word. So successive approximation is in general much more efficient as compared to the digital RAM. But if you're using digital RAM and if your input voltage, of course, is close to the first level, then it's going to take less number of cycles for digital RAM as compared to successive approximation. So, but in general, successive approximation, you already know how many cycles it's going to take to generate a voltage. So these two you discussed in digital 2. Now the third one that we're going to discuss in DSP is Flash ADC. And the good thing about Flash ADC that it basically takes a cycle to convert one input into its digital equivalent code, because all of the bits are converted at the same time or are produced at the same time. How does it work? So in your book, this is from your book, I have put some annotations on this to make it understandable. So this is a 2-bit flash converter, Flash ADC. The reference voltage is 5 volt. So remember, reference voltage of an ADC basically is the highest voltage. So any input that you want to convert, that must not exceed the reference voltage. So any input you're giving, it can maximally go up to 5 volt, but it cannot exceed 5 volt. So this Vin right here, input voltage, it has to be less than or equal to 5 volt. Okay. All right. So now we have a series network of 4 resistors. And why I'm calling it series, when you see that you have a connection going from here, and remember, if you have a connection, you assume if a current is flowing, then two resistors will not be in series. To be the resistors to be in series, they have to have the same current flowing through them. And the reason we are calling them in series is because these comparators that you see, C3, C2, and C1, basically they are made out of, in general, operational amplifiers or any amplifier which have very high input resistive gain. So in general, there is no current flow into these amplifiers or these comparators. So this current is zero basically. This current, where I put this, it's zero. This is zero. So hence there is no current flowing into the comparators. Hence these resistors are going to appear to be in series with each other. So when they are in series with each other, then we can calculate what is the voltage drop at each of these nodes. I did not mention these nodes. Let's say this is node A, this is node B, and this is node C. So what is the voltage drop at A, what is the voltage drop at B, and what is the voltage drop at C? And since all of them are series, we can easily apply voltage division to find the voltage drop at each one of them. For example, at node C, this is the voltage drop across resistor, the bottom resistor is going to be the voltage at node C. And how you're going to find that out? Using voltage division. Since these four are in series, it's going to be VR, the total voltage across the series combination, times the value of the resistor across which you are trying to find out the voltage drop, R, divided by sum of all the resistor in series, 4R. So the voltage at node C is going to be VR over 4. Likewise, the voltage at node B is going to be the voltage drop across the bottom two resistors in series. So you're going to add these two resistors in series, 2R, and apply the voltage division, VR times 2R over total resistance 4R. So it's going to be half of VR. And likewise at node A, now you are calculating the voltage drop across the bottom three resistors in series. So you're going to add three resistors up, 3R, divided by all of the resistors 4R. So the voltage drop at node A is 3.75 volt. Okay, so once you decide that, what is the function of comparators? Basically, comparators take the input voltage at the non-inverting input or the positive input of the comparator and compare that voltage against whatever the voltage is at the inverting input or negative input. If the positive value, that is the input voltage, is greater than the negative value, that is the reference volt or the voltage at node A, B, and C, then the output of the comparator is going to be 1. But if the input voltage is less than the the node voltage at the negative end, negative input, then the output of comparator is going to be 0. So in general, if V positive input is greater than V negative, then the output of comparator is going to be 1. Otherwise, it is going to be 0. So that's how the comparator is working. Each comparator is working. Okay. And then we have 3 NOT gates. Of course, the function of NOT gates everyone understand. They change 1 into 0 or 0 into 1. So input is opposite than the output. And then we have 2 AND gates, and everyone know how AND gate works. An AND gate, basically, as long as both the inputs of AND gate are 1, then the output will be 1. Otherwise, the output is going to be 0 if any of the input is 0. And then the output of each of this output becomes the input of the encoder. So I'm calling them the most significant, or the first input is A3, or the most significant input is A3, A2, A1, and then finally A0. And the output of the encoder is 2-bit. It's a 2-bit converter. So the outputs have 2 bits, output 1 and output 0. Most significant bit, output 1, and then the significant bit, output 0. And we're gonna discuss what is inside the encoder as well. So how does this work? Let's move on, or I can just stay on this page and explain it to you. So let's say any voltage that is between 5 volt and greater than 3.75 volt, right? you have any voltage which is greater than 5 volt, which is 5 volt or less than 5 volt, but greater than 3.75 volt. Your comparator C3 is going to produce 1 because the positive input will be greater than the negative input. So your comparator C3 in that case is going to produce 1. Let me go ahead and change the color of my marker. So comparator C3 is going to produce 1 if your input voltage is 5 volt, but between 5 volt and greater than 3.75 volt. So the output of the comparator is going to be 1. This one is going to carry it from here, and A3 is going to be 1. It's going to go through NOT 3. It's going to become 0. Alright, what about the output of C2? Again, the positive is greater than the negative because negative is 2.5 and positive is greater than 3.75. So the output of C2 is 1. This one is going to go here. So AND 3 has 0 and 1. The output of AND 3 will be 0. This one is going to go through NOT 2. It's going to become 0 here. Right? And then C1 is going to be the same thing. Since the negative input of C1 is at 1.25, positive will be greater than 3.75. So it is going to be 1 here. And this one is going to be carried over here. So AND 2 output is also going to be 0 because the input is 0 and 1. And then the last NOT gate is going to produce a 0 as well. So your input to the encoder is going to be 1 0 0 0 1 0 0 0. Oops. So that's your A3, A2, A1 and A0. And then the output of the encoder O1 and O0, we will say that we want the output 1 1. So 2-bit digital code is going to be 1 and 1. This is 0. So this is when your input voltage is what? Greater than 3.75 volt up to 5 volt, right? Okay, I'm gonna go ahead and change the color of my line again. Let's say I choose orange. Now let's assume your input voltage is greater than 2.5 volt but less than 3.75 volt, right? Greater than 2.5 volt but less than 3.75 volt. So what's going to happen? Comparator number 3, input voltage at the positive is less than 3.75 volt. At the negative it is 3.75. So the comparator 3 is going to produce a 0 in that case, right? This is the second case we're discussing, 0. So a 0 is going to go here. This is going to be 1, right? Okay. Now you have greater than less than 3.75 volt, sorry, coming here, and you have 2.5 volt here. So again, positive side is greater than negative side. The output of this will still be 1. So I can still change it. It still be 1. So that's 1 is gonna go here, and this 1 and 1 gonna go through AND 3, and the output of AND 3 is going to be 1. Right? So second case is done with the orange color. Likewise, C1 input is what? Less than 3.75 volt but greater than 2.5 volt. So this positive input will be greater than the negative input. Output of C1 will still be 1, and it's gonna go through AND 2. Oh, by the way, when this is 1, this is 0, this is 1, so this is gonna be the same. It's gonna be 0 again, and this is gonna be 0 again. So your next case is gonna be 0 1 0 0 input of the encoder, input to the encoder. And we say that, okay, for this the output code we want is 1 0. Alright, let's go ahead and discuss the third case. You understand what's going on basically. So when you do the third case, I don't have to go through each and everything, but for the third case, basically what you see is you will have 0 0 1 0, and for that the encoder should produce 0 1. And for the fourth case, let's say you have 0 0 0 1, and you have 0 and 0 as the output of the encoder. So now you have 4 digital codes. For this one, any input voltage greater than 3.75 volt, the code that will be generated will be 1 1. 3.75 greater and less than 5. Any input voltage between 2.5 and 3.75, the code that will be generated is 1 0. For the third one, any input voltage between 1.25 and 2.5, the code that will be generated is 1. And then the last case is any input voltage which will be less than 1.25 volt, the code that will be generated is 0 0. So that's how the flash converter is working. It is producing the output bits in the same cycle. All the output bits are converted, all are generated in the same cycle, as opposed to successive approximation or digital ramp. Okay. Now, how does this encoder work? So to produce this output, basically we look at, again, the encoder logic you discussed in Digital 2, how to design an encoder. It is extremely simple. Observe that when output 1 is 1, then A3 is 1 when output 1 is 1, or A2 is 1 when output 1 is 1. So A3 or A2. So basically all you need is an OR gate, and connect the OR gate to A3 and A2, and that's going to be bit number 1 at the output. And likewise, you see when O0 is 1, O0 is 1 when A3 is 1, and O0 is 1 when A1 is 1. So you're gonna take another OR gate, connect A1, and then connect A3, connect A3, and then the output of this is going to be O0. So that's how the encoder logic is. Extremely simple, right? That's how O1 and O0 will be generated. So I hope you would have understood this thing. Whatever I explained on just this slide, I have basically put this whole explanation in the next 3 or 4 slides, each and every case. So you can go over those as well with my explanation, and hopefully it will make sense to you. This table I discussed with you, and finally the design of the encoder is discussed with you as well. So go over this thing. Observe, I did not mention one thing. Observe that we are not really using, if I go back to that, you can see that we are not really using A0 to generate the output of your encoder. A0 is called redundant input to the encoder. You don't need it. All you need are the 3 inputs. So you don't really need A0 to generate the output of encoder. Whenever all 3 of the inputs are 0, A3, A2, A1, then A0 will be assumed to be automatically 1, and the output that will be generated will be 0 0, of course, from these 2 OR gates. Okay, so go over it, and then I hope you would understand Flash ADC.